So let us move on to something called an extended relational algebra. So this is extended, so it does increase the power, so it increases power over basic, increases power over basic relational algebra. All right. So the operators here is, there are three operators. First is called a generalized projection. The second one is aggregation. And the third one is called outer join. So at least from the names, it can be guessed that this is a generalized projection. That means it has got something to do with the projection and tries to make it more generalized. So it tries to extend its power. Similarly, outer join is some form of a join, but with something more, and we will see exactly what are all of those things. And of course, aggregation is something new. So let us go over each of these in a little bit more detail. So the first one is generalized projection. All right, so what it does is that it takes the projection operator, the normal projection operator. So the normal projection operator allows only, it names certain attributes and just selects out those attributes. It just projects out in only those columns. So what the generalized projection operator does is that it allows arithmetic operations on those projections. So arithmetic operations on the projected columns. And what do I mean by that? So it essentially says that it's defined like this. This is a function f1. So you can define some k functions over the expression. So these are, instead of just names, these are functions. So these are generalized arithmetic operations, or generalized arithmetic functions. So for example, if we take this example, suppose there is R, which is defined as A, B, and C. Now suppose what I do is I do something like this. So B minus A and C on R. First of all, the schema for this becomes B minus A and C. Why is that? Because this schema, these are copied. Essentially this is the first thing and this is the second attribute. And B minus A, so B minus A, so it's done from here. B minus A is 0, 5, fine. Then this is 2 minus 1, this is 1, 5. Then this is again 1, 5, so this goes there. So there is nothing new is output. And this outputs 2, 8. So these are the answer. And now, well, you can change a little bit on this. So instead of this thing, you could have said 2b minus a, then this would have become 2b minus a by c. So from this would have produced 1, 5. The second one would have produced 3, 5. The third one would have produced 4, 5. And the fourth one would have produced 6, 8. So you can see that any operation can be done. Now instead of 2b minus a, you can do lots of other things, etc. But this is how the generalized projection. So this is where the generalized part is, because it works on any function. So generalized projection, that's how this works. The next one is aggregation. So it lets one aggregate. So it can use certain aggregation functions such as average, mean, max, sum, count. So that is what it does. So and it can be applied on tuples, or more importantly, it can be applied on groups of tuples. So I mean, so this can be applied on the entire relation or on certain groups of tuples, and these groups can be defined, and certain groups can be defined as well. How do the grouping is done? So the generalized form of this aggregation operation is, it can be written in this manner. So there is this generalized g function, and let me try to write it there, and you are applying some functions f1 on A1 and so on and so forth. So you can apply some n functions on this, and the grouping is defined using some grouping operators, grouping values, which is G1 to Gk. Of course, this is on some expression here. So what it means is that this expression E is first taken, and then the grouping is done using this G1, G2, K. Then for each group, where each group according to this G1 to Gk, each of these functions are applied. Then F1, A1, F1 on the attribute A1, which is part of G1 to Gk, F2 to up to F2 on A2, Fn on An, that is when applied. Now, how is this grouping done? This grouping is done, so tuple T1 and T2 are in the same group if they agree on all G1 to Gk. They must agree, so it's for all of them. So essentially, this everything has to be same for T1 to T2. All right. Now, what does that mean? Okay, so let us again take an example. That's the best way of understanding it. So let us say this is ABC. There is a relation R, ABC. So now you are doing this operation. Let us say G sum over C. That's all that is being done. First of all, the schema that is produced is simply sum of C. That is what is being done. And what is being done is that just the sum over. So let me explain what is it. There is no grouping here defined. That means that every tuple is in the same group. So everything is in the same group, and essentially just the column C is summed up. So the answer to this is, that's it. This is the answer to this. Instead, if you try to define a little more complicated query for as, suppose you say G is being done, sum C, that is fine, but with an A. Okay, so by the way, I should say that this is of course on R, and this is also of course on R. So what is being done is this is the following. So the first of all, the schema of this is A and then sum C. Why is that? Because this grouping is done on A, so all the tuples must agree on the A value, and that A value is written here, and then the corresponding sum is done. So how do we do that? So first of all the tuples that agree on the A value, so that means these two are in one group and these two are in the second group. Now for these two, the A value is 1 and the sum is just this, which is 10. For these two, this is 2 and the sum is 13. Now suppose there were another tuple, which is, what would have happened is this is in a group by itself, so this would have been simply 3, 9. Alright, so this is the answer to this query of the aggregate operation with this grouping. That is what it is being done. Let us see the final operator in this space is that of outer join. So in outer join, what happens is that it is an extension of join to retain, so it is an extension of the normal join that you see, join to retain more information. Fine, so how do you retain more information? Is that it first does the join and then adds tuples to the result. Now this seems to be very interesting, that how can it add tuple to the result which is not defined as part of the join. So for the first it computes the join that is given as part of the condition of outer join. It adds all those tuples that are part of the join, then it adds certain more tuples. Now what more tuples? This requires the use of something called a null value. And we defined null earlier in some connection, that null is a part of every domain, etc. So null can be considered to be the value for any attribute of any tuple. This is the speciality of null. Alright. Now let us define one at a time. What is it? So suppose we first define what is called a left outer join. So this is called a left outer join. Fine. So this is denoted by R. This is an interesting operator, this is the join operator with theta. Because this is left outer, there are two strokes on the left. So this is R, left join S. So what it does is that it retains every tuple from left relation. Now which is the left relation? Of course this is the left relation because this is on the left of this, or left, or you can say the first relation. It retains everything from the first relation, even if it does not obey join condition, even it is does not obey join condition theta. Still probably not very clear as to what is happening, but what is happening is essentially this. So let us probably take an example that is the easier way to understand. Alright. Now if we do a natural join of R join S, simply natural join. Now what happens is if you do the left join of S, what it does is that it first completes the join, which is 1, 5, 7, 2, 6, 8, and then it retains every tuple from the left relation, even if it does not obey the join condition. Now which is the tuple that it doesn't? So this tuple has already been captured as part of the join condition, this tuple has already been captured as part of the join condition, but 3 and 7 is not captured. So it must retain 3, 7. Of course this is A, B and C. 3, 7. The question then comes is, what will happen to this value of C? It has got nothing defined, but then the power of null comes. So it essentially says if nothing is defined, it is null. So the answer is 1, 5, 7, 2, 6, 8 and 3, 7 null. So this is a special value that is being used, and this is the left join. So now that the left outer join has been defined, it is probably easier to define the right outer join, which is essentially the same thing except the left here is replaced, the left of the first relation is replaced by the right relation of the second relation, and everything else is analogous. So now just to complete the example, the right outer join for that same example is this way. So first of all, the operator is written this way again, and it has once more it has the same schema as ABC. Now once more, first of all, the first thing to do is to complete the join, which is 1, 5, 7, 2, 6, 8. Then what is left out? So this is captured from the right relation, this is captured from the right relation, this is not captured, so this needs to be copied down. So 4 and 9, and this is padded with null. So that is the right outer join. Now that right outer join is defined, so there is something called a full outer join, which is the combination of both right outer join and left outer join. So this is the operator for this, and it captures from both left and right relations. So once more, going to that, if we go back to this example of 1, 5, 2, 6, 3, 7, then the complete outer join S is defined as A, B, C. So first we complete the join, which is 1, 5, 7, 2, 6, 8, and then we complete the left and right join. So this is 3, 7, null, and 4, null, 9. So everything is completed from, so these were the things that were left out here and left out there, so that both find their way in the full outer join. Now that these outer joins are defined, so the normal join is sometimes called an inner join. The word inner is now understandable because there is an outer join. And sometimes the word outer join, this outer part, outer join, the outer part is omitted. So then what you essentially get is a left join, because there is no left outer join, a right join and a full join. Fine, because there is no left outer join, right outer join, and a full join. And when no theta condition is specified, when it is just the word join is used, when simply the word join is used, then it translates, it is generally meant as a natural outer join. So this is just a part of the terminology. Fine, all right. So then there is a little bit left about this relational algebra queries, which is the special value about null. So we have already seen how null are useful, etc. And null is a special value. So it essentially denotes an unknown or a missing value. And we saw in the examples in the outer join that when A and B are joined, we do not know what the value of C is, so it's an unknown or missing, and that is being denoted as null. Okay, so now this null, and let us see what the aggregate operators ignore null. So aggregate operations simply ignore null. But what happens with arithmetic operations? Arithmetic operations may require comparisons such as 5 equal to null, 5 greater than null, etc. So what happens is that, so for example 5 equal to null, this evaluates to null, or 5 greater than null, etc. So all of these things evaluates to null. So a comparison with a null generates another null. A comparison with a null, there is one very interesting exception, which is null equal to null. This evaluates to true. So null equal to null is actually true. So the three-valued logic. So using null generates to a what is called a three-valued logic. So we have been all used with binary logic, which is using 0 and 1, but there is a three-valued logic. The three values are 0, 1, and unknown. So essentially true, false, and unknown. So these are the three values. And let me write down the rules for all of this three-valued logic. So first of all, the OR table. So OR is unknown or true evaluates to true, because there is a true and it doesn't matter what the unknown is. Unknown or false evaluates to unknown, because the false doesn't matter and this is the unknown, that is it. Unknown or unknown, that evaluates to unknown. The AND is similar. So unknown and T is unknown, unknown and false is false, unknown and unknown is equal to unknown, and the not is there. So not of unknown is equal to still unknown. So this is the three-valued logic table that we require to move forward, and the select operation treats unknown as false. So I mean, if there is something unknown, then the select operation will not select it. That's what it will be meant. Okay, so that completes the part about the queries of this relational algebra, and we will later go over how to use relational algebra for database modifications.